Hi, this chapter is regularization. Actually, in the previous chapter, we talked about optimization, and in the optimization, we didn't talk anything about regularization. Okay, so we just optimized the objective functions. And now in this chapter, we're going to talk about regularization. And first of all, we have to talk about what the regularization is and what kind of techniques we can have and what is the benefit of regularization. Okay, and then we're going to talk about how we can understand these regularizations in detail. And this is the outline of this chapter. First of all, we'll talk about underfitting and overfitting. Okay, and then we'll talk about many regularization methods. First, we'll talk about the feature selection. And then we'll talk about shrinkage methods, which includes rigid regression and the loss regression. And we will understand these shrinkage methods with Bayes' point of view too. And then recently in deep learning, early stopping is one of the most popular regularizers. So we'll talk about it. And then adding noise, including dropout or drop connect or weight noise. Okay, so all these methods can be categorized into adding noise method. And then finally, we'll talk about data augmentation briefly. First of all, underfitting and overfitting. So I think you're already familiar with this figure, and given these samples, okay, then we want to estimate the relationship between x and y. And the simplest model would be a linear model, okay. Then this linear model cannot capture the relationship between x and y. So this model is underfitting the data. And let's take a look at this one. In this case, this model is a lot more complicated than this linear model. So with this model, the training error is 0. So this model fits the training data samples perfectly. But this is too much. Think about this one. When we have one new sample around here, then this model will give us this much error, right? So this model is overfitted to the training samples. And this one is better than the other two models because the model is smooth and it can capture the important relationship between x and y. Okay, so when we define a model, then it could be underfitting, or it could be overfitting, or it could be in the middle of these two extreme cases. Okay, and there is an important concept here, Occam's razor. So when we have a couple of different hypotheses or different models with the same performance, then the simplest one would be the best. That's what Occam's razor says in the machine learning. And here's behind the story of the earthquake that occurred in Japan in 2011. There was a huge earthquake, and when they built a nuclear power plant, and they got all the earthquake data samples from Japanese history, and they analyzed the data samples, and based on the analysis, then they estimated the relationship between the magnitude of the earthquake and the frequency. Okay, so these are the samples, and then they made a model like this. Okay, so based on this model, the earthquakes of at least magnitude 9 occurs about every 13,000 years. So look at this point. Magnitude 9.0 will occur. Let's say if it is 0.0001, then means um, magnitude 9 will occur about every 10,000 years. Okay, so they built the nuclear power plant, which can withstand earthquakes of magnitude 8.6. 8.6 is around here. Let's draw a line. Okay, and let's say this one is 0.005, which means magnitude 8.6 will occur about every 200 years. Okay, so that's what they did. But the 2011 earthquake was magnitude 9, and that devastated the plant. With the same data samples, if we have the model like this, a little a simpler model, then it says the earthquake of at least magnitude 9 occurs about every 300 years. Okay, so if that's the case, then they had to build the power plant which could withstand at least magnitude 9 point something, so around 9.5 or so. So there are lots of factors and issues, but this graph says that their model was overfitted to the history data samples. They had to apply some regularization. Regularization means the model should be smooth enough. Okay, so if it is overfitting, then the model is too bumpy with too much spikes. So if they applied this regularization to their model, then maybe they could avoid this kind of disaster. Okay, anyway, that's the difference between this overfitted model and smooth model. So now we know overfitting would be a big problem. So to avoid overfitting, there are a couple of different approaches. First, we can make the model architecture simpler. Okay, so if we increase the model complexity, then there is a potential to have overfitting. So we can have a small model. But if the model is too small, then it cannot learn good patterns. Okay, so that is another problem. So we have to find the proper size of complexity. Okay, and then next we can focus on underlying abstractions or explanatory factors. Something like a PCA would be helpful. Okay, dimension reduction, or we can select some features based on some other methods. So we'll talk about it. And then we can put some constraint on the parameter space. Okay, so we can actually regularize the parameter space explicitly. So shrinkage method puts some constraint on the parameter space explicitly, and the early stopping doesn't put some constraint explicitly, but when we understand this early stopping, so the parameters are updated and then we stop. Even the parameters are still updating, but we stop. Okay, so the parameters cannot move too much. Okay, so we are actually putting some constraint on this parameter space implicitly. Okay, and then the next one is to spread out the probability mass from the training samples. Okay, so if we have infinitely many samples, then the model cannot overfit, right? So with a small number of samples relatively, and the data manifold is kind of sparse. That's how the model can overfit to the samples. And if we add some noise, then we actually spread out the probability mass over the data manifold. Or we can think of data augmentation. Okay, basically we just make the data manifold smooth. That's another way to avoid overfit. Now, when we talk about the model selection or overfitting and regularization, then we have to talk about the bias variance trade-off first. And I already talked about this thing before, but let me go through these lines in detail. So there is a trade-off between bias and variance. for regression problem. So this one is the output and this one is input, and we have a function f, and this is a true relationship between x and y. And even with this true relationship, then when we observe the data, then there is noise. Okay. Then what is the error of the model? So f of hat is our model. So we trained our model. Then y minus f hat of x is the error actually. And we define our error in this way: the squared and expectations. Okay, that is our error. And in this case, we can replace y with this equation. So now we got this line. And then we can rearrange these quadratic equations. Okay. We just extracted all the terms from this square. Okay. And we can use this term. Okay. Expectation of epsilon is 0 because the noise has a 0 mean. Okay, and then this line goes here, and then we add this term and twice, and we subtract this term twice. So basically these two equations are equivalent. And let's focus on these lines. Then we got here, and then we have these terms here. So we just simply rearrange this line to get this one. And then if we look at this one, then we can get this quadratic equation, and this one can make this quadratic equation. So this is our error, and we can decompose this error into bias of f hat and variance of f hat. Look at this one. This one is the bias, the definition of a bias. Okay, and this one is the bias square. And this one is the definition of a variance. Okay. So we just decomposed this error into bias square and the variance and sigma square. This is an irreducible error. Even with perfect model, we cannot remove this error. But if we have a better model, then we can reduce a bias, or we can reduce a variance. Okay, and there is a trade-off between the bias and variance. Okay, so if we increase the model complexity, then bias square would decrease, but the variance would increase. Okay, so there is a trade-off between these two. And we can use another diagram to explain this bias and variance. So let's say this red cross is the true parameter. Okay, this is the true. And when we estimate, then the result is around here. Okay, in this case, we got the best model. So we have a low bias and low variance, which means we have a low error. But we have other cases here. When the variance is low, but we can have a high bias. Okay, so then the sample is around here. Okay, so in this case, the bias is high. Okay, the expectation of this is around here, and there is a difference. But the variance is small. But in this case, we have a low bias because this is true. But when we take an average or expectation of these points, then the expectation is around here. So this has a low bias, but these samples have a high variance. And in this case, we have a high variance And when we take an average, there is a big difference. So we have a high bias and high variance. So this is the worst case. And this is the best case. Okay. And when we have a high variance, then we have an overfitting problem. Then we can use more data and we can make the model simpler, and we can use bagging. So in the ensemble model, we talked about bagging and boosting, right? So bagging could reduce the variance, and the boosting could reduce the bias. Okay, so when we have a high bias, then we have underfitting problem, many cases. And in this case, we can use more features and a more complex model, and we can use boosting. Okay, so this is the big picture of bias and variance trade-off. Okay, now let's talk about the model complexity in linear regression. So I think you're already familiar with linear regression. And linear regression is a simple and interpretable with good performance. Okay, so adding predictors always decrease the training error. Okay, it means we have more features and we can increase the model complexity. And then always we can decrease the training error with the bigger model. Okay, and then adding predictors does not necessarily improve the test error because we might have a fitting problem. Okay, and selecting significant predictors is hard. Okay, when we have a lot of features and predictors, and which ones are important and significant to predict the output. And it's not easy to select the significant predictors. So given x, and when n is smaller than d, then there's no least squares solutions. We need more samples. Roughly, in some algorithms like ICA, then n should be at least 2 or 3 times bigger than d. Okay, but it depends on the applications and algorithms. But at least n should be larger than d. Okay, so when n is smaller than d, then we cannot get W because this one is not invertible. Okay. It's not possible to check all possible combinations. If we know, if we can check all the possible combinations, then we can select a few features. Okay, so then we can decrease the D. So there are a couple of approaches to select the features. First, subset selection approaches. So we can use forward selection and backward selection. Forward selection is simple. We can start with the one feature. So we can try all the features, and we can evaluate all the features, and we can choose the best feature. Let's say in this case, the x2 is the best feature. Okay, and then now we have d minus 1 features. Out of d minus 1 features, we can add the next best feature. So now we have x2 and x5. And we can keep adding these features one by one. And backward selection goes the other way. So we can start from all the features, and then we can delete 1 out of 5. So when we delete x2, then we got the best, the performance. And from this, we delete one more, then this one is the best feature set. Okay, and this one is too naive, so we can have a plus L and minus R selections. We can repeat the following steps. Apply forward a selection L times and apply backward selection R times. Okay, so then we can increase and decrease and increase and decrease. that would be much better than these simple directions. And also we can use cross-validation for each step to evaluate which one is better. Or we can apply the model complexity criterion like Akaike information criteria or Bayesian information criteria or minimum description length. Okay, so these are model complexity criterion. And the second one is dimension reduction approaches. So we have too many features compared to the number of samples. So we have to reduce the dimensions. Okay, so in this case, we can use PCA or some other methods. So first of all, we apply the dimension reduction algorithm, and then we apply the regression on the projected space. And then if we need, then we can reconstruct to the original space.